Hello, everyone, and welcome. Thank you all for joining us today for this live stream event. My name is Albena, and I'm the program manager of the Microsoft Reactor San Francisco. I will be sharing session resources with you in the chat, but before we begin, I would like to quickly review two items with you, our code of conduct and our event guidelines. First, please take a moment to review our code of conduct. Microsoft Reactor seeks to provide a respectful environment for both our audience and our presenters. We do encourage engagement in the chat, but please be mindful of your commentary, remain professional and on topic. And secondly, our event guidelines. This session is being recorded and will be available on demand through the Microsoft Reactor YouTube channel in about 24 to 48 hours. Which brings us to today's session, Resiliency at Scale with Netflix Conductor. We have our speaker, Viren, the CTO and co-founder at Orchest. We're going to welcome him right now. Hello, Viren.
Hi, everyone.
Thank you. Please take it over. Thank you.
All right. Thanks. Hi, everyone. Thanks for joining. And today, we are going to spend some time in the next 45 minutes to 1 hour talking about resiliency at scale. And we'll talk a little bit more about what does it mean to when we think about resiliency, when we think about scale, and how do we kind of handle both of these scenarios with something like Netflix Conductor. So with that, I would like to start the session. So with a small quiz. It's always fun to start with a quiz time. So here is a question and something to kind of think about it. Are you building distributed applications? I'll just pause it for a second here. I would like you to kind of think about it and see what do you think. But let's dive a little bit deeper into this question, right? When we think about an application architecture, does this sound familiar to you? You have microservices, you have stateless functions or containers, service communication over various RPC protocols like gRPC or even plain old HTTP, and some sort of asynchronous communication. It doesn't have to be all of these things, but maybe one of or two of this. Is this how you build your applications? And if the answer is yes, then yes, you are building distributed application. Why is it so? Because if you now think about it, right, you have application with various services and components that are distributed over the network, that are communicating over a network protocol like gRPC over HTTP, could be a PubSub with Kafka or RabbitMQ, and that starts to kind of build very much like a distributed application now. And all the regular philosophies of a distributed computing kind of applies here, right? Like things like, for example, network is going to be limited. Failures are going to be norm. And how do you handle that? How do you build applications that are resilient in terms of the network failures, in terms of service failures? How do you scale them, knowing that things are not going to be completely infinite? There are going to be limitations to the network. There are going to be limitations of the downstream apps and services that you rely on to complete your work. And not only that, right? If you think about building an application, it's not just about implementing your business logic. Take, for example, let's say I am responsible to build an application that helps me implement an entire flow for checking for or implementing the fraud resolution flow in a bank. So, in an ideal world, I would like to just kind of go ahead and implement all the necessary business logic that kind of accomplish that. But it is typically not just that, right? Like beyond business logic, you also have to figure out how do you coordinate the work across different services. If you have microservices or service component based architecture, the moment you kind of go distributed, how are you going to handle the business transaction across different services? And we talked about it earlier, but how are you going to handle transient and persistent failures? Not every failure is same. Some failures are very much transient in nature. Think of them as like jitters in a network. They happen for a blip, a second, and then they all normalize. So if you do retries, things will be okay. Some of them could be persistent. Service is down for an extended period of time. what do you do at that point of time? Does everything fail? Do you kind of work with the reduced capacity, or service availability? Like, what happens there? And last but not least is, you start to build a distributed application with a flow that is spanning across multiple services. How do you provide visibility into the overall execution? How do you know where things are failing, where things are taking more time? What does my path look like, and things like that. And then when it comes to scaling distributed applications, now you have to start thinking about the scenarios where your services are running at a very massive scale, or even a very high scale, right? How are you going to manage these pipes, which are either plain HTTP services or asynchronous service buses? What about the backups and retries when things fail? What about rate limits? What if one of the services is talking to a database and you can only do so many requests per second before the database tips over and starts to kind of introduce failures? How do you kind of handle that? And to be able to do that, like, how are you going to handle the back pressure when you get 100 requests per second but you can only serve 50 requests? What are you going to do? Are you going to reject the request? Are you going to throttle? Are you going to kind of hold the requests in a queue somewhere and then process them as they complete? Depending upon the use case, any of those things could be applicable, and how are you kind of going to implement those things? And finally, in an environment where your workload could be unpredictable, how do you auto scale? And it goes both ways, right? You scale up or scale down. So take, for example, let's say if you are processing orders, if you are responsible for order management service, um, maybe during the holidays you have to scale up, and once the holidays are over, you can scale things down, because the volume is going to go down. And then let's think about what happens after the application is built. When you think about the life cycle of an app, there is the part where you are working with a product manager or a business analyst in coming up with the spec, designing the app, coming up with the detailed design, implementing, testing, and all of those things, right? And pushing it to production. But the life does not end there. It kind of goes beyond that, right? What happens on a day zero, from day zero to day 100, when application is live in production? The engineers and developers who had been working on the app have moved on to different projects, maybe different companies, and the application is the responsibility of the people who are responsible for operations. How are you going to handle documentation? We all know one fact is that the documentation is outdated the moment it is written. So how do you kind of keep it up to date when things go wrong, and they will go wrong? How do you provide the visibility into application state as to what's going on right now, where things are failing, how to handle those things? And when that happens, how are you going to handle those one-off scenarios for fixing the state? Take, for example, you were supposed to make an entry into a database. A database was having a problem. This entire process kind of failed or put things into database in a wrong way, and you want to retry all of those operations, so that, like, you can fix the state. Now the question is that, are you going to write one-off scripts for it? And if you have an app with 10 different steps, this could be a pretty large number of scripts that you have to write in advance, if you want to handle every possible scenarios. Or you do this when that happens, right? So that brings up to the last point, which is, how do you manage the tooling for operations? Do you build essentially bespoke tooling for every application that you are building? And that might be okay if you are build one application a year, but what if you are building a new app every month? I will not go through this whole thing. You can read it, right? But when you think about distributed applications, there are other complexities also involved. Um, Unreliable network, multiple transport protocols, failures becomes a norm, not an exception. Um, the connection complexity can increase if you are making point-to-point connections, and like larger the number of connections, harder it becomes to visualize the application flows. So let's talk about some of the kind of pitfalls that introduces complexities, that does not help you scale applications as much as you would like to. One of them is service coupling. One is when you have services which are coupled with each other in terms of versions. So service A calls service B, and it understands what version of service B is running into, and you have to make sure that um, service A always calls service B with the specific version, or there is a lock-safe deployment process. You can't deploy a service without impacting other service that relies on it. And then comes the routing part, right? What happens after you make a call to service A? uh, what happens next? Who makes a decision as to which service should be called next? And then you start to embed routing logic inside application code. And not every application calls are synchronous, right? Some of them could be long running, and you are relying on a message bus, and there's a single message bus that everybody listens to. What happens if this message bus goes down? um, and that starts to kind of give a rise to what we like to call as a distributed monolith. And all of these things kind of gives a rise to an application pattern where you take a monolithic application, you kind of break it down into services, and you thought you built a distributed app with and have broken down the monolith. In reality, what now ends up happening is that you still have that monolith, just that you have distributed it across multiple applications and services, increasing the complexity even further. What we realized was, when you are trying to avoid all of these things, you start writing code and focus on operations and maintenance a lot more than the application logic that actually drives the business. And we saw that it is almost at 70% of the time being spent on doing this, versus actually 30% of the time being spent on the business logic. So enough talk. Let's take an example, right? So we have all been through this. You look at your credit card transaction and you see a charge that you don't understand. So what do you do? You kind of use your bank's app or site, or make a phone call and specify that this is a fraudulent transaction. And this is a very high level overview of what basically happens in the back end. Of course, the reality could be a little bit, and it's probably a lot more complex than this, but I'm trying to kind of simplify this a little bit more here. But the moment you report a dispute on a transaction, it starts by fetching transaction details. You want to check if the transaction is eligible for a dispute or not. What if this was happened 2 years ago? This may not be eligible anymore, right? There might be some limitation in terms of within how many days you have to report transaction, and if so, maybe you just notify the customer saying, hey, this is an older transaction, sorry, we can't do anything about it. Next step is to kind of get probably the customer details to see who you are for the bank. Are you a high value customer? And the main reason here is, a high value customer, you want to keep them happy. You want to check what's your monthly average balance, and if it's within the limits of the charges, just reverse it, right? Like, you want to keep the customer happy rather than try to kind of get them through multiple hops and processes. But maybe not. Then you want to probably assign an agent here, and now it's no longer an automated process. You have a human agent kind of who's assigned this particular task, is going to look at the transactions, maybe make a few phone calls to you or maybe the merchant, I don't know, and eventually decide whether what should be done. And then maybe transaction is reversed, maybe not, but either way, the outcome is kind of sent back to you via email or SMS or whatever modes of communication that you have specified with the bank. It's complex enough, at the same time it's simple enough, right? Like, if I think about building an app, all the purple boxes are ones which I need to implement. Some of them are database transactions, some of them are API calls to services that can send out an email or SMS. Agent dispute could be something of a UI app that is built bespoke to be able to handle all of these things, where they can look at the transactions, click a button to say approve, reject, and so forth. So how do I go about implementing this, right? We'll start with the language, right? Of course, depending upon the engineering practices, we'll pick a basic language, Java, C Sharp, Go, Python, any of those. Implement all the purple boxes. wire up the flows, deploy this on your kind of deployment architecture. It's a lot of companies are today relying on Kubernetes, VMs, even bare metals. You run test, involve testing teams, business analysts, product managers, run through the testing and fixing cycle until everything is kind of looking good. And finally, what you relax and move on to a different project. But wait, is that how it is? You also got to figure out a few more things, right? Before you start implementing the business logic. How are these services going to communicate? What if the service itself is down? Like for example, let's say I'm using a service that is responsible for sending out emails and or SMS to notify the customer. And what if the service is down? Where do I halt my application flow? Oh, as you can see, right, this could be a long running process, especially if an agent is involved, and this could run for multiple days. Where am I going to maintain the state, and how am I going to coordinate across multiple services and communicate back to the customer? All of these things I was going to figure it out. And one more thing is, when you think about the applications and processes, they are never static. As in, you come up with the original flow, implement it, deploy it, and move on, and that remains like that forever. Not in today's world, right? Things are constantly changing, competition is there. Maybe you want to introduce a chatbot using LLMs now. That's how what everybody's trying to do now, right? What if you want to use a machine learning model to detect whether this fraudulent transaction can be automatically approved or not, based on various input parameters? And maybe you want to experiment before you kind of roll it out. How are you going to do all of these things, right? Like that's and it's constantly changing, right? Maybe you want to try a new thing every 3 months, see if it works, see it improves the customer satisfaction or the amount of money that is being spent on reversing transactions, um, and whether it's working or not. So change is what is constant here. It's constantly changing. Time to market is critical. You are competing with other banks, other service providers. And when you think about changes, right, not every change is a code change. Sometimes you just want to rewire things. Maybe you want to first send out an email and first then do something else. Just rewiring service flows here and there. Do you want to spend time, more importantly, precious engineering resources, kind of doing those things? That's another thing to kind of think about when you think about scale. And finally, self-documenting flows, right? If this was the state of the application on day 0 and even day 1000, great. But as we saw, right, like that's probably not going to be the case. Things are going to change, things are going to evolve. And when do they happen? Who is responsible for maintaining the documentation? Like, how do you know what's the current state when the PMs who originally worked on, the business analysts who originally kind of came up with the flow have moved on to a different project, different company? Who has this knowledge, right? And last thing you want is just a bunch of tribal knowledge, or having to look into the code every time there is a request to check what's my current flow, right? And how about the scale? Like, if I am responsible for maintaining this service in a production environment, as an SRE, if you have SRE kind of practices, how do I know when should I scale up the service or scale it down? Like, what are the metrics that I should look at? Where are those metrics? And I also want to know the uptime, right? There are multiple services, there are multiple components involved here. What is their uptime? What is their SLA? How is it all handled? How am I going to handle the operational complexity? Let's say I'm responsible for the support teams, who's maintaining the support for the application. And when a customer call comes saying that, no, my fraud dispute query that I had kind of registered, let's say 2 weeks back, hasn't been resolved yet. How do I know where is it stuck? Is it stuck because it tried to make a call and it failed, and it is just hanging in there, or is it waiting for some agent to kind of respond on it? Like, what's the current state? How do I know what's happening with the system? Now, if you kind of boil it down, when you think about it, right, like we have long running processes, we probably have shared services, things like, for example, email or SMS send. It's not specific to this application alone, right? Like, there are going to be multiple applications which are relying on them. The customer information database is definitely shared, which means that many other apps are also querying that. You want to make sure that, like, no, you are fair to all the applications. and avoid any problems where a bug in an application could cause the database to bring down. You probably want to integrate with machine learning systems. You might have third party integrations. And finally, if you think about it, right, it's not purely automated system. There are also humans in the loop. And how do you kind of handle those things? These are all non-functional requirements that you have to take care when you start kind of thinking about implementing this. So I tried giving it a shot and see, like, if I were to build one component of this, right, a small piece of one of the diagram here, in say Java or C Sharp, how is it going to look like? Um, and all the to-dos that you see here, right, are all the error cases. How am I going to compensate when things are executed only partially, and reverse things? Or how am I going to introduce rate limits here? How am I going to wait for somebody to kind of complete, or an agent to kind of complete, and then kind of move on? It's not straightforward anymore, right? Like, there is a lot more stuff to do. Um, Now, one often overlooked aspect of any business application is versioning. If we say that, like, the applications are not static, they are constantly evolving, then just like we version control our code, and we have tags and versions, what about my application logic and overall flow, right? Like, where is that version handled? And you don't want to DDoS your internal services or databases, right? So you have to make sure that you have right rate limits in place, you have retries in place, and there's a lot of these things, right? This is where 70% of the time kind of goes into, rather than implementing the business logic. And as you can see, right, like, none of this is actually implementing business logic. Business logic is fairly straightforward. This is where the complexity kind of arises. So we started thinking about, right, this is an insightful thing. These are the problems, but there has to be a solution, right? So what if there was another approach? And in some ways, like, we started thinking it is like, what if we could just implement the application exactly the way we drew the workflow? Like, I don't have to think about everything else. Like, I can build an app with assumptions that network is reliable, that services do not go down, that databases can handle millions of QPS, that I don't have to worry about rate limits and all, and I can just write stateless code, put it together, and it just works, right? Uh, so yeah, of course, like, this is not something kind of new. Orchestration has been around for a while, and orchestration sagas are a very well-known pattern. And that's exactly what I want to kind of focus on. And this is what we solved, right? What we did was we implemented an orchestration platform. It's called Conductor, and we built Conductor to solve these problems. And the idea was exactly what I described, that I should be able to write applications exactly the way I draw the diagram, um, write stateless code, write services that are following single responsibility principle. I shouldn't have to worry about all the aspects of complexity and scale in terms of being able to handle retries, rate limits, failures. All of those things should be handled by somebody else. And that's exactly what Conductor does. Given the fact that it's a pretty general purpose orchestration platform, we open sourced it. It's available under Apache 2.0 license. There's a link to the GitHub repository. You can certainly check it out. Um, Give it a star if you like it. Um, Now, what were the design principles that we came up with when we decided we wanted to kind of build Conductor, right? As I said, it's not a new pattern, which means there has to be products out there, platforms out there that solves the same problem. So why create a new one? So oftentimes what happens when you introduce a component like an orchestrator, that becomes a single point of failure. If your orchestrator is down, your entire business comes to a halt. So one most critical point here was that there cannot be a single point of failure. So it has to be purely a peer-to-peer distributed system. And all the communications should happen through persisted distributed priority queues. All three are important points here, right? Persisted, so that, like, even if the orchestrator itself goes down, which it will, given the fact that it's running in a distributed environment, in a cloud environment, uh, data should not be lost. And priority, because not every process has the equal priority. And if you're a single orchestrator, it is important to be able to prioritize the workload based on the business need. So the priority becomes an important aspect of it. The other piece is that all the routing is done by orchestrator. If I were to write single responsibility stateless services, my services cannot do the routing, right? My services then becomes purely transactional, in the sense that I get a request to do X, I implement the logic to do the X and produce the output, and I'm done with it, right? What happens next, what happened before, what if I produce a failure, all of those things should be handled by orchestrator. My service should not really know anything about it, right? The other piece is that we live in a heterogeneous environment. A lot of services are existing in an environment today, exposed over HTTP or gRPC. I should be able to leverage them and plug it in, or I should be able to write simple worker code that can easily plug it into the ecosystem. I'll quickly glance over this and skip over. Uh, but Conductor essentially does that, right? It allows you to define service flows in multiple ways. You can use the UI to design the entire application flow, um, or if your flow is completely dynamic in nature, you can write the whole thing in a code, um, and now your code becomes the entire workflow. So that's the power of Conductor, where you take the code and your code becomes resilient. Second piece is that it's completely polyglot, so you don't have to necessarily come up with a specific language and stick to it. You can mix and match, which is kind of today the reality, right? Let's say most of the business logic part of the application is probably going to be in Java or C Sharp, versus when you think about UI interactions are going to be in JavaScript. ML interactions are typically written in Python, and Conductor allows you to do that, right? Um, we wanted to make sure that it supports polyglot nature of the application development flawlessly. And of course, you just write the business logic code in the services, and it takes care of the rest, right? In terms of making sure that the service calls are durable, um, and you can handle compensation. And this is an important aspect when you think about a distributed application. You don't have a notion of a two-phase commit. That's not even possible. Let's say if your application flows are running for hours or days or months at time. So how do you kind of handle the persistent failures? And typical process for doing that, and the pattern for doing that, is through compensation. So Conductor allows you to kind of handle compensation flow. When things go wrong, you can go back and reverse the transactions. It is an eventually consistent system in the end. More importantly, it gives a very interesting superpower to your application. When you think about an IDE, when you are writing the code and you are going through the debug process, right? You can actually see step by step what really happens, right? You can inspect the variables, you can see why certain code paths are taken, and Conductor lets you do that at runtime. Every execution is captured, which means that you can search for those executions to see what happened for an application for customer X. You can visualize the entire call graph, so you know exactly what path was taken, if there were decisions, branches, parallel executions, what really happened there. And if things had failed, you can actually retry and rerun things, right? Think of this as like a tape recorder, right? Which you can kind of pause, rewind, restart, anything of that nature, and you don't have to write the bespoke code for it. It can do it automatically for you. And finally, goes without saying, right? If it was developed at Netflix, it had to kind of work at a scale. So let's take a look at it, right? Like if I were to implement the same fraud dispute flow in Conductor, how is that going to look like? So on the left, what I've done is that now I've tried to kind of put together a Conductor workflow, achieving the same thing that we saw earlier in a diagram. And as you can see, right, like it is exact representation of what I draw, and this is actually a functional code that actually runs and executes. So it's not just a diagram; it's actually a piece of code. The whole thing is designed in Conductor. There are services that are HTTP calls, which are wired using the built-in tasks. So I'm not writing new code to make an HTTP call. I mean, that thing is done and dusted for a long time now. There's no need to rewrite it all the time. And specific business logic is all exposed, which is not exposed over HTTP call, is written through workers in Java or C Sharp. And all my workers and services are stateless. Now, here is an important aspect of having a stateless system is that it's easy to scale stateless services because they don't have to maintain a state. They are not backed by a database. You can scale up, scale down much easier. At the same time, it's also easy to change them. You can just version control, create a new version of it. An interesting thing about Orchestrator is that Orchestrator also knows which services are being used and what versions are being used, which means if I've got three versions of a service and I want to replicate the version one, I can instantaneously know who is using version one, go back and ask them to kind of migrate over. And once I'm confident that nobody's using it, I can safely shut it down. So I talked about, like, how do I, it makes it easy to write workers, which are basically services written in Conductor. So here are some code snippet, right? And as you can see, it's a very lightweight way of doing things. One thing that when we were designing Conductor was we did not want to impose a new framework or a way of doing things for developers. And the idea was you should be able to work with your existing frameworks. So if you're using Python and using Python Django, Java Spring Boot, Golang, it should just work. And you should be able to kind of interplay all of these things depending upon what suits the best to handle a particular task. And the SDKs in Conductor that way are very lightweight. They are available in Java, C Sharp, Golang, Python, Node.js, even Clojure for that matter, if you are a fan of functional programming. And then think about some of the cases like how do I handle long running workflows? Conductor workflows and applications can complete in, let's say, 10 millisecond to 10 months, anywhere in between. And it can kind of handle very long running workflows as well as synchronous short duration workflows. If you were to sometimes wait for a certain period of time, let's take an example of a subscription renewal service. Once a user signs up, you want to probably wait until the end of the month or the first of the month before you send a reminder. And in a typical application code, you will put um, an entry into database somewhere, run a daily process, query the ones that needs to be modified or updated, and then do some work. Right? With Conductor, you can avoid all of these things. You can just have a wait task and say wait until maybe say Christmas, for example, and then send out a blast email to everyone saying, hey, here's a new Christmas discount, for example. You don't have to worry about writing any bespoke code for handling all of those things. Similarly, if you were to kind of handle rate limits, you can just specify in the configuration itself. And the idea behind configuration is that, when you think about configs as code, you can independently change version control and deploy your configuration from your code, and they remain separate. So we talked about building distributed applications. We talked about Conductor. So how do I kind of go about building applications with Conductor, right? So there are three parts to it, right? So there is a notion of a workflow. A workflow is what defines the application state. When we looked at the fraud dispute flow, for example, right, that's my application state, how things are kind of wired, how they are routed, all of those things, right? Essentially, workflow acts as a distributed transactional backend for your application. Your workers are what actually implements the business logic. These are stateless components. They are language and platform agnostic, even framework agnostic, right? They are deployed outside of the orchestration plane and runs on pretty much anything that you can imagine, right? Anywhere from Kubernetes to VMs to bare metal on your laptop, on IoT devices, anywhere you can run code, the workers can run. And then finally, you have your applications. These are, let's say, front-end applications using Next.js, React, mobile apps, or purely backend applications. They use Conductor APIs to kind of kick off the workflows, manage their state in terms of being able to terminate them, retry if there are failures, and so forth. And essentially, the applications leverages Conductor as its state management backend. And that's basically the high level of how you build apps with Conductor. And if you think about it, right, essentially what conductor implements is an event driven orchestration. The events are happening, and as they happen, the decisions are made on the server side. Next set of tasks are scheduled, and things kind of move forward from that point onward. So just to repeat, right, like with conductor, all the communication between services happens through persisted distributed queues. There are no direct calls. Services do not communicate directly. All the routing is done through the server itself, including handling the rate limits, retries, failures, all of those things. And the entire application state is managed by conductor, and it provides a very rich set of APIs that allows you to kind of query the state of an application instance, manage the state if required, and so forth. This is a very high level diagram that shows the architecture of conductor. As I said, right, like you have a notion of applications that you are writing to solve a particular business problem. They are using APIs to talk to conductor server. They execute workflows, get the status, and show the appropriate things in the UI or as an application. You have workers which are responsible for executing the specific tasks, and things like that. Now, one of the superpowers of conductor is that it has a very rich UI, which is an operational kind of UI that allows you to do two things. You you have developers working with the UI to design the conductor workflows, if you choose to. You are also able to kind of go into the UI, search for specific executions, monitor, debug, all of those things, right? It helps you greatly reduce mean time to detect and failure, and resolve the failures if there are. At the same time, for operators who are responsible for managing the application at runtime, it also gives them a state of the visual representation of the overall application state, which means that it makes it easy for them to understand where things are, various metrics, which service needs to be scaled up, which service has a high failure rate, all of those things. And behind the scenes, your orchestrator is completely stateless. It's responsible for constantly evaluating the state as the events are happening in the system. And it has a built-in powerful scheduler, which means that no, you can actually schedule different workflows to run at a periodic interval, which is useful for background jobs and things like that. All the state is maintained in a very flexible pluggable database store. All the executions are indexed, so you can search for those things. And the core to this, the pipelines, or the highways through which everything kind of communicates and talks, are the distributed queues. These queues are built as part of conductor. These are zero configuration queues, so unlike many other queuing systems where you have to kind of have an admin endpoint to kind of configure the queue, manage them, conductor is a zero configuration approach here. Queues are created and tear down depending upon the workload, and you can have thousands and thousands of queues sitting in a server with almost zero cost. This is slightly higher or deeper level architecture. One other thing conductor does very well is third party integration. As the saying goes, right, like no system is an island. They always talk to other systems. And what that means is with conductor also we built capabilities to be able to integrate with various other systems. So it plays very nicely with third party or external event handlers, things like SQS, RabbitMQ, Kafka, Service Bus on Azure and GCP. It integrates very nicely with the storage providers, like S3 or Azure or Blob Store on Google Cloud. Same with metrics. So that kind of provides a very rich, healthy ecosystem of integrations, letting you kind of build applications that spans across multiple kind of domains. So going back into conductor's design principles, what it does is conductor workflows are eventually consistent. They provide at least once delivery guarantee, which means if a task is scheduled, it's guaranteed to get executed. Worst case scenario, when there are failures, it will get redelivered, and it provides all the right metadata for the workers to understand that this is a redelivery of the message, and then they can take appropriate actions to address those things. Let's say if your workers are not idempotent, they can use the idempotency key to identify and uh, a completed transactions, and avoid rerunning the same transaction, which could have side effects. The last but not least, Conductor is very much API driven. So there are APIs for doing pretty much everything, which means it's pretty easy to integrate with various systems through APIs, as opposed to kind of having to work with the UI and things like that. So that's about Conductor. We are almost at the close of our presentation. So how do I get started with Conductor? Right? As I mentioned, Conductor is an open source project. It's available on GitHub. So please do visit, give us a star. For the repository, we have a Slack channel. I have kind of put in the link here. But feel free to join the Slack channel. We are typically online there. Happy to answer any questions you might have, and help you out. Orcus was created by us to bring Conductor as a cloud-hosted service in various clouds, including Azure. Um, uh, you can check it us out at orcus.io. If you don't want to figure out how to run Conductor locally on your machine, we have a playground that allows you to kind of safely experiment and try it out. You can visit play.orcus.io, give it a try, and yeah, look forward for any more questions that you might have. Since we don't have more questions, let me take some time, and I can kind of give you an overview of what does it look like to build. Um, all right. So this is we have talked about Conductor. This is essentially the UI that I was talking about, and I'm going to show you is some of the capabilities of Conductor. So like as I said, right, like it indexes all the data, so you can actually take a look at it, visualize the application code. So for example, here is a small workflow that I can use it to send out an email or SMS to a user, right? It queries the user information, finds out whether the preference is to send an email or SMS, and based on that, it will send an SMS or email. It's a pretty straightforward and simple workflow, but it can get really complex. You could have a lot more complicated flows which contains sub workflows as well. So like for example, here this is a workflow that is much more complex in comparison. Does run few things in parallel, waits for them to complete, uh, another kind of parallel execution, runs a loop along with a decision embedded inside, has a workflow that is called as part of the workflow itself, so it allows you to kind of build a very modular approach to it. And more importantly, for every task, I have full visibility into what's happening with the system, right? When was it scheduled, when did it start, when did it complete, overall duration, the host on which it ran, the inputs given to it, the outputs it produced, any logs that might be the case. So when things go wrong, it's much easier to kind of go and look at, and I can go and retry where it left off. It also gives me a timeline view of what's going on. So if I were to kind of look at the overall execution flow and see where the deficiencies might be, where is the room for improvement. I can take a look at it and see what's going on. Here I can see, for example, this loop takes almost 2.5 seconds to run, mainly because there is one task that is taking much longer to execute. Now, which one is this? This is the one. So I can go and fix this if required. That's the UI. Thank you all. If there are no more questions, I will leave it at that. As I mentioned again, do visit us on various channels, and see you online. Thank you all.